a warm welcome from my side to this webinar about Kungsbacka. Just to remind everyone who's participating, this session is going to be recorded. And with participating, you kind of agree that your comments might be recorded as well. Great. So we have 3 speakers today. The first of them is Krista Killasju from Extra. He has been a CEO of the municipal housing company Extra for 13 years. And Krista is a construction engineer who has worked in the industry in leading roles for 25 years. And an important part of his leadership is to enable Extra to continue to innovate, constantly develop, and both individuals in the company and the company itself. And the ENFLATE project suits him because it's challenging and exciting. So it suits him well. So hi Krista from our side as well. The second speaker is Nicholas from Noda, and he's a system developer and DevOps engineer at Noda. He works with a wide range of solutions, often in a customer-oriented and project-related context. Nicholas has a background in full-stack development and engineering, as well as sales, coaching, and management for several exports teams. Nicholas also works in music production and is interested in developing and maintaining corporate culture. The last speaker of them will be Dmitry Romachenko from IVL, who holds a doctoral degree in energy systems modeling and analysis. He has 10+ years of work experience in the energy sector and is currently the team leader for the energy systems modeling experts at IVL. He has participated in multiple projects, mainly focused on district heating systems, waste heat recovery, flexibility services, and sector coupling, demand, response in buildings, and the value of storage technologies in energy systems. So, hi as well to all 3 of them. And before we start, we're gonna show the video of Firas. And just let me share my screen for that.
I think the sound is not on.
Oh, I'm sorry for that. Let me fix that. Does it work now?
Yes.
Thanks.
För oss på Extra är det ju jätteviktigt att ta nästa steg inom hållbarhet. Vi har varit väldigt framgångsrika länge inom solenergi, energieffektivt byggande med våra passivhus och biobränsle. I detta projektet handlar det om att kombinera dessa 3 saker så optimalt som möjligt och även involvera våra hyresgäster. En av de största utmaningarna och huvuddelen i det här projektet är att få då flexibilitet mellan de här olika energislagen, solvärme, biobränsle och el. Och få dem genom smarta tekniska lösningar, genom AI, att kunna verka tillsammans. Och till det även addera våra hyresgäster, att deras beteende kan styras över tid, vilket gör att det blir en win-win för bägge parter.
Nej, men sms:et gör ju att man blir mer uppmärksam på när det är dyrare på dygnet eller billigare, så man vet ungefär när man kan spara lite extra och inte behöver sätta på tvättmaskin eller diskmaskin eller vad det nu är.
Och till slut också är att skalar man upp sådana här små projekt så kommer det också avlasta så att säga, nätet utanför området. Det kan både vara elnätet eller fjärrvärmenätet genom att vi är så effektiva med timing och utbud inom vårt område. Det är det vad det här projektet går ut på i stora delar.
We from IVL Swedish Environmental Research Institute contribute to the ENFLATE project by studying long-term development of energy systems. In particular, we focus on flexibility issues and synergies between district heating and electricity sector. So in this particular project, we develop and apply energy system optimization model. And then this modeling we apply to the demo site, to the actual Fieros area. So the focus of the modeling is to study how the energy system will develop in the future by taking advantage of all the flexibility resources available here. We do it with the objective of scaling up the modeling to other cities and other regions in Sweden and abroad. In addition, the modeling results will help local decision makers, for example, the local district heating company, to make long-term sustainable investment decisions so that we reach the goal of climate neutrality together and in good time.
Det vi på Nordea gör här på Kungsbacka-anläggningen är att vi optimerar energitillförseln och även efterfrågan. Och det är bland annat baserat på elpris, prognostisering eller andra önskemål. Genom ständig optimering och samverkan mellan de olika energikällorna baserat på exempelvis pris och efterfrågan säkerställer vi ett balanserat inomhusklimat samtidigt som energisystemet förbrukar mindre energi. Vi styr elpannan, vilket i sin tur värmer upp varmvattnet och som sedan då skickas ut på returen igen, vilket då avlastar värmesystemet också.
Great. So with that, we have the first part, and whoever wants to like review the video, it is also uploaded to the ENFLATE official YouTube channel now, or I'll just put the link in the chat here. And yeah, from now on, I think, Krista, the stage is all yours.
Thank you, Stefan. Thank you for that introduction, and I will continue to Is it in the right presentation mode?
Yep, it's all great.
Yeah. Thank you. I will tell you a little bit more about this demo site in Fieros, and first I will take some facts about Ekstra, who is owned by the municipality of Kungsbacka. So we have around 3,400 apartments and 200 premises, but it's not so common. But we have our own district heating department in about 20 biomass plant, and we use the energy. 50% we use by ourselves, and the other 50% we sell to the markets to other real estate owners. And we have lots of passive houses, lots of solar energy, both PV and solar collectors. We worked with solar energy for almost 50 years, and we have very lots of solar energy and biomass fuel. The most we burn with wooden pellets. Quite small company, around 52 employees, and Kungsbacka is on the west coast of Sweden, south of Gothenburg, you know, that west coast. And Fieros, where you see the red arrow there, is a small town outside Kungsbacka. And it's actually Ekstra was founded there for 60 years ago. So it's back to where we started. And this demo site at Humlevägen in Fieros is a mix between normally apartments. You see this 4 buildings built as passive houses. And we have this substation in the middle. I'll come back to that later. And we have retirement home, group housing, preschool, property office for our own employees, maintenance people, and also you can see the biomass plant called Ögärdet, who is delivering district heating to the whole Fjärås network that Dima is going to tell a little bit more of later. And what is a bit special here as well at Humlevägen is that we have our own microgrid. So all the buildings are connected to a microgrid electricity network, so we can move the solar energy from the buildings to buildings when the demands is different during the day. So that's quite unique in Sweden that we can do that. And in this particular project, the substation here is actually the heart of the area, and it's from the beginning it's just a substation for district heating, but now they have this also the microgrid is also run from the substation. So that, as I told in the movie, this for us is to optimize the energy. We have solar energy, we have electricity, we have district heating, and this was we like to optimize it. What kind of energy produce is the best for the time? Is it best to run it with electricity when the price is low? When there lots of sun, so we use the solar collectors and the PVs, and otherwise the district heating. So we installed an electric boiler to this big water tank. So it was installed, I think, was in the middle of the winter, and we'll use lots of time and to make it, lots of tests to make it works. So now it's so that if the electricity price is low, we are set 50 or maybe 50. If the price is low, the electricity boiler is goes on and heat up the tank with hot water. If the price is high, and we have the district heating warms up the tank, and if it's a sunny day, the solar collector warms up the tank. And if it's just absolutely maximize everything, they also we send out that on the district heating. So this substation is now actually a part of the energy system, producing energy out to the district heating network. So that was one of the most technical things, but something is very important for us is how can we engage and use our tenants to be a part of making this project work. So if we can make the tenants move the consumption of electricity or district heating during the day, it was benefit us a lot. So we took 14 of 16 households was involved in this. They got a text message the day before. Let's just see at this example to right there. Tomorrow between blah, can you use the electricity on other times, and see if that's changed their behavior. They didn't benefit anything from this, just to make them understand that the electricity price is very ups and down during the day. So this project was made by a student from Stockholm University, Isa Diamant, for the nudging flexibility. I think maybe Dima can show it. I think you can read her results somewhere in this ENFLATE project. And what's next for us in Fjärås, Kungsbacka? We're going to install dishwashers and washing machines who can run both on hot water and electricity, so we can make this thing flexible even for this these machines. I hope we will do this thing very soon, and we can make it work maybe by itself, or we will have something to connect with the tenants so they can do that choice. But we'll be back to that later. And I think that was my last slide. And we take the questions at the end, I think. So we summarize together with Dima and Nico. So should you, Nico, share the screen, or should I continue?
Yeah. Thank you for that, Christer. I'll go ahead and share.
Yeah. So now it's yours.
There we go. Right. Hello, everyone. Thank you for tuning in. So my name is Nicholas, and I work at NODA Intelligent Systems. And we're going to talk about our platform a bit and what we have done and what we are about to do as well. So I'm going to tell you about NODA in ENFLATE. And NODA is a Swedish-born innovative deep tech software as a service company with patented technologies and proven solutions to accelerate the uptake of digital intelligence in the energy market. NODA enables energy companies, property owners, and industrial partners to accelerate and excel in their transition to radically more efficient energy systems by providing digital solutions for advanced decision-making and control within demand, supply, and distribution. So in ENFLATE, NODA is developing and testing hybrid control technology to optimize the operations of different coexisting heat sources, such as district heating, solar power, and electrical boilers, while ensuring quality of service to residents and tenants. So a little bit more about creating and managing data access. Our platform layer includes an extensive set of capabilities required to build a fully functional energy management system for digital solutions in the Kungsbacka demo. This includes, but is not limited to, the following components: a single tenant database system based on PostgreSQL, authentication based on IDP, identity provider, and REST-based API, enabling external systems to interact with the platform, and tools to configure and administer services and users, report creation and management, including template tools for easy scalability, solution integrations for communication with controllers, building management systems, sensor communication protocols, and other IoT communication standards, and also microservices backend architecture. So more about hybrid control optimization. In the district flexibility optimization platform, the functions of the hybrid control are manifested in the 4 core concepts of forecaster, which creates forecast of the heat demand and available thermal flexibility; the planner, which creates control plans based on current forecasts and system constraints; the tracker, which distributes control actions among the connected buildings; and also the Vader, which is the software agent for each individual building or other flexibility sources. So the concept of the Vader stands for Virtual Distributed Energy Resource. And in ENFLATE, we have the following things that have been developed and will be further developed as well. So we have the planner. So it's a 5th optimization model focused on the Kungsbacka case with general applicability. The tracker updated the BDI model for focus on the desire. And the Vader tariff control functionality, which returns temperature optimization and Sigma model creation. The Sigma model represents the Vader's desire to perform control actions. So next steps in our platform and in the ENFLATE project will be to deploy and evaluate the developed enhancement in the district flexibility optimization platform, train the models on the data available in the system, perform active control during the coming heating season. So that is what we have in our 4 hours. So thank you for that. And questions will be summarized at the end. Yeah. Thank you.
Thanks a lot. That was quicker than we thought. But yeah, so the next speaker is going to be Dmitry right away.
Okay, I hope you can hear me and you can see the slides.
Yes, both perfect. Thanks.
Okay, hello everyone. I mean, if you are a bit quicker than we thought, then I don't think I will need to be stressed in order to finish my presentation earlier. and that also doesn't mean that I will just talk for 40 minutes. But long story short, my name is Dmytro Romanchenko. I'm working at the IVL Swedish Environmental Research Institute. I'm so sorry, I will be looking a little bit toward this way because that's the screen with my presentation. But today I wanted to let you know what are we doing as a research institute in this project, and that is we are taking a bit of more of a research hat on ourselves, and we are trying to understand the long-term development and long-term implications of having more flexible district energy systems. So if I click and I show the next slide, I hope it will work now. Okay, I cannot change the slide now. So I will talk about today a bit of an agenda, and that's district energy and flexibility, and specifically district heating systems. I will introduce you to the objectives of the work. I will talk a little bit about the optimization modeling frameworks that we are using, some input data, and of course the results of the modeling that we are having so far. So if you jump directly to the next slide, this is a schematic representation of what we mean by district heating as presented by Energy Force, which is a Swedish agency, but I would actually argue that this is not just a representation of district heating, that's more of a representation of district energy system, which includes a bit more than heating, but also electricity. And what we mean by this is that in general, district heating, for example, means that we would use some sort of centralized heat generation technologies, such as combined heat and power plant or a heat pump, to generate heat and then transfer that heat using the network of pipes to our consumers, so basically to buildings. And when we look at this picture, we can see that some of our technologies, they are available on the supply side, as said, but also we can see that there's available technologies on the demand side, such as small-scale heat pumps here, small-scale thermal energy storages. We can also use demand response, and that all of the things provide the system with some sort of flexibility. So we can run all of these technologies together, and we can run each of them separately quite flexibly. What's interesting in this specific project is that we are aiming to couple heating to electricity. And again, if you take a closer look at this part to the left, we can say that the combined heat and power plant, as the name stands for itself, it can produce both heat and electricity. While, for example, a heat pump, that is a technology that uses electricity to produce heat. And that basically shows us that our heating and electricity sectors, they are tightly interconnected, and we can use this possibility, use this interconnection to provide flexibility to the system itself, but also to the larger systems, such as, for example, national electricity grid. So that is why we are focusing on this in this specific project. If you talked a little bit about district energy and flexibility, so this will be the objectives of the work we do as a research institute. Again, we are trying to focus on long-term development of the studied energy system, and that is being said with the FIEROS energy system, or a district energy system of FIEROS. We are looking at district heating technologies and individual technologies and the competition between them. But the sub-focus here is that we are studying, as said, this connection between heating and electricity, and how these flexibility options that we have in the system, or that we could have in the system, could support the system itself and the surrounding electrical grid. So let's spend a minute on this specific slide. We are working with a specific software, which is called TIMES Optimization Modeling. And TIMES is a tool to create energy system optimization models. So what it constitutes is the following. We start by representing our existing energy system. We call it the reference energy system. And by that, we mean that we include in the model a certain number of demands. In this case, it can be heat and electricity. So we represent the demand in the system in the model. And we represent the existing heat and electricity generation units within the system we study. So basically within the district energy system of FIEROS. What we do next we include the time horizon of up to 2050. So we are studying the system in the long term. We want to understand how these demands in the system will be satisfied in the future, not only today. But this poses another problem. We know that some of the existing heat and electricity generation technologies, they will become too old and we will need to phase them out someday in the future. So for the model, it means that we will need to reinvest in some other technologies in order to be able to supply the demand. In order to do that, we are adding to the model so-called techno-economic parameters of alternative heat and electricity generation technologies. So the model for us will optimize their operation of the units, but it will also be able to invest or suggest new investments in new heat and electricity generation technologies. In order to be successful with this task, we need to provide to the model a number of assumptions about the future demand, about future fuel and electricity prices, because they are coming as external signals to our FIEROS model. We will need to make assumptions on the availability of some sources, and we can also study different policy implications or the developments of the national scale, so changes to taxes or some sort of subsidies. So what we will get at the end, we will be able to study the development of the said energy system into the future. We will be able to see in which new capacities the model wants to invest or doesn't really only want to invest. I mean, the model will provide a cost-optimal solution to the problem. So we will find investments that will bring their lowest possible cost to the system. And we will be able to see the utilization of fuel, how much energy was generated in each year of the way, and even within year. And I will come back to that. And we will also see the respective costs of running such a system. So not only investment costs, but also the running costs of energy system in FIEROS in this case. So this is schematically how the model will function. Now let's try to understand what is included in the specific model we developed and applied to FIEROS. In contrast to what Christer and Nico were mentioning right now, the actual practical demo sites implementations are focused on this cluster here, which is the number of practical existing buildings where we test physical stuff. But for our optimization modeling, we needed to include more buildings, because if we want to optimize the supply of energy, we also need to represent all the demands of such energy. So that is why we included also other buildings which are owned by EXTA and which are having district heating as a main source of heating. And we also included external consumers. These are buildings that are not owned by EXTA, but these are buildings that are consuming district heat in the area. So long story short, if you translate this picture into these schematics, right now in the model we are having 21 archetypical or representative buildings which are consuming electricity and heat. And in the model, we show their networks which are providing these energy carriers, and also the main sources of heat and electricity in terms of generation capacities. And we also included the storages. So long story short, the model can choose what is the best source of heating, for example, at the address of Himmelwagen, and the model can choose between locally produced solar heat, or it can take heat from the district heating network. So that's already a competition in between the sources here, and other buildings are also having either one source or a couple of sources of heat and electricity. So that is an existing system that will later evolve into something new, and soon I will show the results of the modeling. Before we come to the results, this is very important specifically for the ENFLATE project, we needed to make a number of assumptions about fuel prices or demands on the so-called sub-annual level. So not only the energy demand as one number per year, but also what is happening between the hours of the year. For that reason, we have collected information about the heating demand profile of all these representative buildings that we have included in the model, and we have presented it by having 1 week from each season representing the whole year. Or in other words, we are representing the whole year with using 4 weeks from each season, and each of these weeks has hourly time resolution. So we are having 672 hours in each modeled year. So that will be schematically our winter time with the demand during winter. This will be spring, summer, and autumn respectively. In addition to the heat demand profiles, we also have electricity demand profiles. And if you look closer, we can see that these are different types of buildings, because these buildings have demand during their evening time, and some buildings have demand during their first part of the day. So this is very important. We can study different behaviors of buildings. And finally, one of our main assumptions is the future electricity prices, which of course we don't know how large and how fluctuating will be the prices in the future, but we can test different profiles. And that's why we are doing the modeling. So this is the assumptions we have in the model as of now. Now let's get to the first modeled results that we are having. So in this figure, we are seeing the capacity of the local district heating grid. And that means that right now in 2022, we have 2 wood pellets fired boilers in the system, and we have 2 gray ones. These are oil fired boilers in the system. So this is the existing capacity of the system as of now. What we are doing in the reference case, we are saying that oil fired boilers will need to retire between 2030 and 2035. So here they disappear. But pellets-fired boilers will disappear after 2040. And what we are doing next is that we are forcing, in this case, the model to make a reinvestment in exact same capacities. So that will be our base case. What will happen if we continue to produce heat in the area as we did before, as we do now? So this is how it will look. But when we let the model make an investment on its own, so we are making it free for the model, this is the result that we are getting. So again, we are seeing phasing out of the existing technologies by 2030, and another step by phasing out technologies in 2040. And we are seeing that the model suggests an alternative optimized solution. The model says that in such a case, it would be cost optimal to invest in some sort of capacity which will use biogas, so we could provide the peak capacity in the system. But when we lose more and more existing heat generation technologies, the model wants to invest in other types of generation. And that will be a heat pump, which uses outdoor air as a source, and wood chips boiler. You see, we also have capacities which are smaller as it is nowadays. That also means that a lower total capacity in the system will be able to supply the peak demand even during the coldest winter days. So we can also save a little bit in terms of capacity. However, the interesting point is, how do we actually operate these new capacities in the future? Do we really use a lot of biogas in the future, as is shown in the capacity figure? Again, this is only the capacity installed. Now we will check how much energy or how much heat we are producing from these boilers. And again, historically, and in this reference case, we see that mainly we use biopellets in the system to generate heat. So other types of boilers, they are only serving over for a short period of time in each year. But in the alternative case, we remember that the model have suggested to invest in a lot of capacity using biogas. However, it does not suggest to use a lot of biogas. So even the smaller capacity of heat pumps will be generating most of the heat in the future. So we are seeing a nice combination of different technologies which could provide the same amount of heat in the future, but using the optimum or the best points in time when we want to run them. And again, this is a nice combination from the point of view of coupling it to the electricity grid, because again, the heat pumps, it's a technology that utilizes electricity to produce heat. And that means that we can use low price hours of low price electricity and to run heat pumps to produce the heat locally. Finally, this will be one of my last slides. We can also check what is happening in each year, in each hour that we are using in the system. So if that is our base year, we are seeing that between hours, this is how we want to optimize operation of our technologies. And that is mainly pellet boilers and a little bit of solar collectors on tops. But when we look in our alternative scenario and we are taking this assumed year of 2050, we can see that the model sees these dips in electricity prices and tries to optimize our wood chips boilers and heat pumps in accordance with the electricity price. So when the price of electricity is lower, we are, I guess this will be the best example. During the low price periods, we are using our heat pumps at the maximum. But when the electricity price goes higher, we are trying to use wood chips at their rated capacity and then follow our demand for heating using our heat pumps. So basically, their conclusion is with high electricity prices, we are maximizing the output of wood chips. With lower electricity prices, we are closing down or we are temporarily shutting down our wood chips units and we are running the heat pumps in order to make sense or in order to benefit from these electricity prices. Let's get to some of the outcomes. So we have developed a times model and applied it to the area of Eros. We did test the long-term system development of the system. We can say that the future tells us that it will be nice to interconnect electrical and heating systems of the area more by installing at least heat pumps in order to create a coupling between electricity and heat. And that is another solution that we are seeing, but I didn't have time to show today, that our existing solar panels and the storages are also used to provide flexibility. But in the future, we want to add to the model new options, and new options will be investments in small-scale electricity and heat generation. So we will also see the competition not only between district heating technologies in itself, but district heating versus individual technologies. And we want to test new investments in heat and electricity storages. Finally, in the project, we will also run multiple scenarios, as the one we showed today that was the base and one alternative scenario, but we want to test different prices and different technologies in the future, so we will create a plateau of different scenarios. Yeah, I think I will also stop here, and we are now 40 minutes into the webinar.
Thanks a lot, Dimitro. And yeah, with that, third of 3 presentations, the stage is open for questions. And yeah, if there is none so far, I would have a question for Krista. As far as I see it, there are 3 different approaches for optimizing the system. And the one is simply you just keep nudging the people and tell them, hey, turn on your washing machine or something, like early in the morning or middle of the night or something.
Yeah.
And I mean, if you train them long enough, they're just gonna do it automatically, perhaps, if they're just good people. This is like the behaviorism approach. The second one would be the entrepreneurial one. You just tell them, hey, you pay less if you let it run now and not later.
Yeah.
And the third one would be like the AI one. You just simply install smart gadgets everywhere, and then they just put in their laundry and it runs whenever it runs, and they don't really have to stress about. Is there any, because I think I saw like more or less the first and the third one approaching, is there any long-term idea which one of these you're going to choose, which path you go?
I think that the best one, or was most successfully for a long time, is the third one. When the tenants don't actually have to do anything, it runs automatically. If we can get so far with the technology and I think that would be the best one, and I hope we can go there with maybe with the help of Nicholas and everyone. So maybe you can have some of the tenants who is interested to do this because they are good people or whatever. But for the main part of the people who lives us, I think it's much easier and better if it works automatically, I think.
Okay.
So that they also can pay less because they buy electricity from us and they buy hot water from us. So they also can see it on the monthly payment that is they pay less if we use this smart technology, I think.
Okay, so that's the biggest nudge you can get to just
I think so.
money. All right.
Yeah, money is I think I think so.
A great motivation always.
Yeah.
All right. So there are no questions so far in the chat from anyone else. If someone wants to stand up. If not, I would actually have a second and third one both. Sorry, other two guys for Krista. One is in Germany, most people are focusing when they're on like smart grid and everything, they're just focusing on charging cars. Is that I just saw laundry and washing like dishwashers. Is charging cars also something you thought about in the yeah?
Yeah, we have that. We have charging our own cars, our own personal our maintenance people who run the cars, electricity cars, and also the attendants. We have maybe 20 charging station in this area. So that's included as well because if you charge your car in the night or it's much better than doing in the day.
And how does that practically, like, you put your car there at 8 p.m. and then you just say I'm going to return at 7, just charge it whenever you want, or how does it work so far?
We are not there yet, but we hope you can be. You put in the plug in the car and you say I want to leave at 8 o'clock or something, and I need 50% or 35% capacity of the battery, and then the charge when it's most it's best prices, I think.
Okay. And yeah, the last one would be you said you installed solar panels 50 years ago.
Solar collectors.
Oh, okay, then not that. I thought solar panels, that would be really pricey back then.
Sorry, maybe. But we are also actually we have some solar collectors who is up and running, who is 45 years old. It works perfectly. So I think we were one of the pioneers in solar heating in Sweden.
Okay.
Yeah.
Okay, great. And yeah, for Dmitro, I would have one question for like I think it was the third to last slide. If you could bring that up again. One before.
Yep. I'm trying to make it happen.
Like the last one with actual data, I think it was.
Yes.
Yeah, this one. Here, there you said in the middle reddish underlined, if the price is really low, you just run on air heat pumps. But I just see that on the first third, like why is then the wood chip spoiler turned on as well?
You mean here?
Yes.
Yes, that's because their actual heat demand is ramping higher.
Okay, sorry.
Yeah, because we are following the demand still, and we do have a little like storage capacity in the system already now, so that is also playing a role. I mean, I couldn't really show all the details as of now, but this is the basic schematic. So yes, here is the jumping, and the demand is higher, and even here we can see 1 hour when the demand is really high. So we even include this biogas boiler which we invested in.
Okay, so the upper line above everything you show is the demand actually.
Yeah.
Okay. All right. Okay. Thanks. Then it was perhaps I was the only one who did not get that from the beginning. I'm very sorry.
No. it was probably me who also didn't explain, but let's see if we get maybe we get some more questions.
Okay. Yeah, I'll just guess we wait for another 1 or 2 minutes, but since I guess everyone had the chance to write a question now, or if anyone is up to say something now. In any other case, we are close to being at 48 minutes, and with that, exactly on time, actually. Yeah, so if there are no further questions from anyone, I would, like to thank you all three again for your talks. It was very intense and very, very nice.
Thank you.
And with that, I'm gonna close this first webinar, and I'm gonna stay in here until everyone is left. So, yeah.